Welcome to Hot Chips 34. Session 1, GPUs and HPC.
Good morning, and welcome to Hot Chips 34. I'm Cliff Young, and my vice chair is Gabriel Southern, and it's our honor to welcome you back to the Hot Chips conference, the 34th time we're holding it, the third time we're holding it virtually, and that deserves a little bit of explanation. When Gabriel and I convened the organizing committee back in January, our outlook on what things would look like this summer was cloudy, and as it turns out, Hot Chips is a relatively small budget conference that depends on academic institutions for our stages, and it was difficult to find a stage that could commit to us for the summer back in January. So we made the decision among the entire organizing committee to wait one more year. I'm sorry for that. I had hoped to be the general chair who presided over bringing Hot Chips back to a hybrid format, but that will not happen this year. Ideally, it'll happen next year under Gabriel's steady hand. So thank you all for coming back. Thanks also to our sponsors who are listed on this slide at all the different levels in which they support us. Their financial support allows us to bring you this conference as effectively and affordably as it is. They have Slack meeting rooms on our Slack workspace, and I encourage you to interact with them. Also, I guess 2 years into the pandemic, giving instructions about Slack seems perhaps redundant, but we do have a wonderful Slack workspace. It is an interactive, somewhat social, virtual meeting room kind of space, and the substitute for our being able to meet in the hallways. They're organized with a key code that's listed on this diagram. And one particular thing is during talks, Slack is how we ask questions. So please do ask questions virtually. Upvote the ones that you like. That helps our session chairs to pick the ones that are most relevant to the topic of a talk, and we'll have great Q&A sessions. And I mentioned before that Hot Chips is a relatively small budget, mostly volunteer-run organization. I will say, as general chair, it's a remarkably good organization with wonderful volunteers in all the different capacities that we put together to bring the conference to you. There's a number of people listed on this website, and even more volunteers who are not listed in depth on the site who work behind the scenes. You can see a diagram of our studio production center in a hotel in Cupertino here. It's a really great group of people. If you're interested in volunteering, we would very much like to have your help in future years. And with that, that is my set of duties as general chair to start up the conference. Now I'd like to introduce our program chairs, Kersta Asanovic and Ron Diamant, who have put together an incredible program for this year. I'm very much looking forward to actually both days and many, many different directions in the talks. Kersta.
Hi, so Krista Asanovic, program co-chair with my co-chair Ron Diamant. We're very excited this year. As always, there's an amazing program. And this is only possible due to the efforts of the amazing program committee we have. So we assembled a program committee from experts across industry and academia. And unlike most conferences, they have to work very hard extracting submissions from companies. And as you'll see, we have some bleeding edge chips that they managed to get from various companies. And so just a wonderful, exciting program this year, as always. So I'm personally struck by the amount of effort that the PC puts into running this show. So thank you to all the members of the PC for helping us assemble such a great program this year. So this is a bit of a retrospective, but yesterday we also had two great tutorials. The first one, Nathan from AMD put together the CXL tutorial that covered a lot of the new features in CXL, especially what's happening in CXL 3.0. So if you missed that, I encourage you to go take a look at the videos. It's all recorded and available. Also, there was a great tutorial on MLIR, a new compiler infrastructure that's being used in many projects ranging from traditional software compilation all the way through hardware design with circuits. So that was just an amazing tutorial. Please take a look at that if you haven't already. And moving on, we're very excited about the two keynotes we have this year. So the first keynote will be later today at 1 o'clock Pacific time. And we have fortunate to have Pat Gelsinger from Intel, CEO of Intel, coming to give us a talk about how semiconductors run the world. And our second keynote tomorrow will be from Ganesh Venkat from Tesla, telling us all about how they build AI systems to run the car and the driving in the car. So that's going to be a fantastic keynote as well. So just amazing this year. Two great keynotes. And I now hand over to my co-chair, Ron, to talk about the program statistics.
Thanks, Kirsta. We assembled a wonderful program for you this year. It started quite a few months ago with a call for submissions, and we got 72 abstracts from across academia and industry. Each one of the program committee members reviewed each one of these abstracts, and we selected 27 talks to be presented to you this year. We arranged the talks in 7 sessions, 3 today and 4 tomorrow, as you can see on the screen. Cliff talked about our Slack workspace. When you sign into Slack, you'll see a window that looks roughly like this. And on the left side, you'll see a set of channels where we have a dedicated channel per talk. So as the talk starts, go into that channel, post your questions. We also encourage you to list your affiliation. And during the Q&A session, our session chairs will pick a few questions and will ask the speakers live to get an interesting interaction after the session. We also typically have our speakers interact with the audience after the session ends via the Slack channels. So we encourage you to stick around, ask more questions. Our audience typically loves this interaction. We also have 16 outstanding posters this year. You'll see links to the slides and a lightning talk format of a video in our website. And you can also see a dedicated channel for our posters where you can interact with the presenters there as well. So ask questions and interact with our poster presenters. There are a few gems there. All right, and that's it. We have a wonderful program this year. We're super excited about it. Hope you enjoy it, and let's start.
Good morning, everyone. Welcome to Hot Chips. It's my honor and my pleasure to kick off the very first session of the Hot Chips 2022 conference. My name is Natalia Vasilieva. I'm Director of Product from Cerebras and a member of Hot Chips Program Committee. The very first session at Hot Chips today will be about GPGPUs. We will have wonderful talks from NVIDIA, AMD, Intel, and Biren Technology presenting their advanced designs for new GPUs. So without further ado, let me introduce the first speaker from NVIDIA. Jack Choquette is a distinguished senior engineer in NVIDIA, where he has led the architecture development of NVIDIA GPGPUs streaming microprocessors for multiple generations. Jack has been leading GPUs and system designs for almost 30 years. And today he will be presenting new NVIDIA Hopper GPU, talking about overview of the architecture, what that can be, how that can be used for HPC and AI applications. Let's hear from Jack.
Hello, everyone. My name is Jack Choquette, and I'm Senior Principal Engineer at NVIDIA. Today, I'm going to be talking to you about NVIDIA's new Hopper GPU. Today, I'm going to cover an overview of the H100 GPU. I'm going to talk about how hierarchy and asynchrony are key components to performance and how Hopper takes advantage to and accelerates them. I'm going to describe how H100 accelerates deep learning with its 4th generation tensor cores and other improvements. And I'm going to finish with a brief preview of how H100 is used in systems to scale up and out performance. Let's start with an overview of the H100 GPU. H100 is built on TSMC's custom 4-nanometer process and contains over 80 billion transistors, which makes it the world's most advanced monolithic chip. The H100 GPU contains 132 SMs, each delivering twice the performance per clock over A100 SMs and introduces multiple new features. H100 also includes a new memory system that features the world's first implementation of HBM3 and a larger L2 cache to deliver a generational leap in memory bandwidth. And to support multi-GPU SuperPod and cloud designs, H100 introduces a variety of new system architecture features. It includes the 4th generation of NVLink and a new NVLink network, our 2nd generation multi-instance GPU technology, as well as new accelerated confidential computing support for secure accelerated computing. Hopper has made many improvements to its SM core. It features a 2x clock-for-clock improvements in traditional FP32 and FP64 throughput. It supports 256 kilobytes of unified L1 cache and shared memory storage, which is 33% more than A100. It contains the new 4th generation Tensor Core that is 2x faster and more efficient. The Hopper SM introduces a new dedicated instruction set for dynamic programming called DPX, which provides advanced operand fusion for inner loop of many dynamic programming algorithms. It adds a tensor memory accelerator for efficient asynchronous movement of multi-dimensional tensor data. Finally, Hopper introduces the biggest shift in GPU computing since the foundation of CUDA, a new level of hierarchy between the CUDA hierarchy of thread blocks and grids called thread block clusters. Thread block clusters enable applications to take advantage of locality in order to dramatically improve efficiency. Hopper's H100 features 5 HBM3 sites with a total memory capacity of 80 gigabytes. This memory system has been designed to maximize not just peak bandwidth, but delivered bandwidth. To achieve this, it features improvements in both the memory as well as the GPU's memory controllers, which were optimized to run at dramatically increased DRAM frequencies and redesigned to include twice as many memory channels per HBM site to maintain the same high efficiency despite the increase in frequency. As a result, H100 achieves over 3 terabytes per second of memory bandwidth, 2x the throughput of our previous generation A100. On Hopper H100, we have made several improvements to our MIG technology. H100 provides around 3 times more compute capacity per MIG than A100, and roughly 2 times more memory bandwidth per MIG. Next, we have added dedicated image and video decoder engines per GPU instance. These are important for AI inferencing customers who often do lots of image or video processing. Finally, in H100, we have combined our MIG technology with our confidential computing technology for secure execution. Here, the trusted execution environment encapsulates one confidential VM running on the CPU with a MIG instance running on the GPU. We took advantage of the physical isolation of units that MIG already provides, plus we added a hardware firewall to prevent any unauthorized access to memory from outside its trusted execution environment, including from other MIG instances. Our PCI interface, we have SRIOV, which stands for Single Root I/O Virtualization. It virtualizes all registers needed to control and program each GPU instance. All transfers on PCIe are encrypted. Each GPU has its own keys, so there's no data sharing between VMs or between GPU instances. By combining MIG and confidential computing, H100 is now the world's first multi-tenant native confidential computing platform using a single GPU. Here you can see the performance for key mainstream HPC and AI models, including many vision neural networks and smaller language networks. You can see that H100 delivers anywhere from 2 to 30 times performance of our previous generation A100 when both use InfiniBand. On top of that, H100 introduces a new NVLink network interconnect. It enables more efficient scaling across multiple GPU accelerated nodes, provides another major boost of performance across HPC and AI application. With the new NVLink, H100 provides up to an additional 2 to 3x performance improvement for HPC and AI training. Now I'm going to dive into the details of just some of the new features for Hopper. First, I'm going to go over some key principles for performance and describe the improvements and features that Hopper has made to take advantage of those principles to improve efficiency and performance. Here are 2 key principles for achieving high performance with parallel programs. One key principle is data locality. By moving and keeping program data as close as possible to the execution units, a programmer can exploit the performance that comes from having lower latency and higher bandwidth across local data. Another key principle is asynchronous execution. This means finding and allowing independent tasks and data movement to overlap as much as possible. The goal is to keep all the units in the GPU fully utilized. Let's look closer at data locality and cooperative execution. There are 2 types of locality we can exploit. One is spatial locality. Here, data and parallel execution have a spatial relationship. Computation can reuse data spatially. One example of this are spatial halo overlap as shown in the figure. Another example is where computation has spatial sharing in one dimension to be combined with data in a different dimension. Another type of locality is temporal locality. Here, data and parallel execution have a temporal relationship. This can be thought of as compute passing over data. First one kernel processes data, and then another kernel processes the data. Let's first review the spatial locality that NVIDIA GPUs currently support. In CUDA, locality can be expressed as a grid. A grid is mapped onto the GPU hardware hierarchy. Computation on the GPU takes advantage of local storage to that GPU. In the case of Hopper, that's 50 megabytes of L2 cache and 80 gigabytes of HBM3 memory. The next level of locality that can be expressed is the thread block that is mapped onto the SM hardware hierarchy. Here, computation can take advantage of a 256 kilobytes of SM localized storage in the L1 data cache plus shared memory. The smallest level locality is threads. These are mapped onto hardware thread lanes. Here, computation takes advantage of thread local register file storage, up to 1 kilobyte per thread. This translates to 64 kilobyte per SM partition and 256 kilobytes per SM. The way work is mapped onto the hardware is by taking the grid of work and breaking it into fragments of work and assigning them to a thread block. The figure shown is broken up in a two-dimensional grid, but CUDA and hardware supports three-dimensional mappings as well. Programmers use whatever is the best mapping for the underlying algorithm. Independent blocks each work on their own fragment of the problem. Within the blocks, there are multiple threads that cooperatively execute on the fragment of work assigned to that block. This three levels of GPU hierarchy has existed since CUDA was first introduced and has enabled parallel programs to take advantage of locality that exists in their algorithms. However, GPUs have scaled by orders of magnitude. Here's NVIDIA's Kepler GPU, introduced 10 years ago. It had 15 SMs. Here's NVIDIA's Hopper GPU today. It has 132 SMs, an order of magnitude increase in 10 years. The entire Kepler GPU could fit in one corner of the Hopper GPU. The Kepler GPU is roughly the same size as Hopper's GPC level of hierarchy. To take advantage of additional locality, H100 has added an additional level of hierarchy to CUDA, the thread block cluster. Here, computation can take advantage of the GPC hardware hierarchy and the 256 kilobytes of localized storage in the SM. SMs within a cluster can communicate directly to each other through an SM to SM network. In CUDA, the thread block cluster is a big block full of thread blocks. You can think of it as a thread block on steroids. Thread blocks in a cluster no longer need to be executing independently. Like threads in a block, the blocks in a cluster can cooperatively execute on their fragment of the problem. This enabled us to target a localized subset of the grid, enabling more opportunities for programmability and performance. In CUDA, a cluster is a collective of up to 16 blocks. Each block is guaranteed to be on a separate SM and is guaranteed to be running at the same time. You can now have a lot more threads and GPU execution resources, all cooperatively working on a fragment of a problem. In your CUDA code, you annotate a kernel with cluster size and dimensions. Just like blocks, the cluster dimensions can be 1, 2, or 3-dimensional. Programmers use whatever best fits the algorithms that's being mapped. The Hopper hardware architecture provides clusters with a direct SM to SM communication network. Using this network, threads in one thread block can directly access the shared memory of another thread block. Accesses are done through a distributed shared memory model laid out as a partitioned global address space. All memory operations are supported, including loads, stores, atomics, and synchronization operations. The communication network also supports accelerated synchronization and data exchange. Threads and thread blocks in a cluster can directly synchronize with each other through barriers in distributed shared memory. It also supports asynchronous DMA operations between thread blocks. Now let's move away from spatial locality to talk about temporal locality. One form of temporal locality supported in existing NVIDIA GPUs is dependent grid launch executing on data in L2 and HBM3 memory. In the figure, you can see an example of a fast Fourier transform workflow. Multiple computation steps are needed to perform the transform, each with a different radix. Here, data is moved into HBM memory local to the GPU. From there, each step is performed by reading data from the local HBM memory, doing the computation, and writing the results back to the local HBM memory so that it is available to the next step. The limitation of this is that each step must be a different kernel launch, as the radix algorithm for each step requires a different configuration of the SM. It also means that between each step, data stored local to the SM must be flushed back to HBM memory. To improve efficiency of temporal locality, the Hopper architecture has added a new capability, thread block reconfiguration. Going back to the FFT example, you can see how this works. There is a single grid launch for the entire transform. For each radix step, the SM thread and register file resources can be reconfigured to match what's needed for the radix step being done at each step. At the beginning of the transform, data is loaded from memory into shared memory and distributed shared memory, and each radix step is performed without data leaving that memory. So instead of execution passing over data in HBM memory, we have execution passing over much closer and more efficient SM shared memory. Now let's look closer at the next core principle for performance, asynchronous execution and data transfer. Let's first review how things work in a synchronous machine design approach. When working on parallel computation, multiple threads will work together and perform that computation. One way to do this is threads can work cooperatively. This is where threads are doing the same computation but are working on different parts of the data. At each phase of the computation, the threads will synchronize to ensure the data they're working on is ready for the next phase of computation on the data. Another way the threads can have a more producer-consumer model. This is where data produced by one thread is consumed by another thread. Here, the consumer needs to synchronize with the producer to ensure the data has been produced and is ready to be consumed. With a synchronous machine approach, all threads must arrive and wait at the bearer until all other threads have also arrived at the bearer. They are effectively running in a lockstep manner. This leads to inefficiencies where thread and execution resources are idle waiting for the bearer to clear. Now let's see how things work with an asynchronous machine design approach. Here, synchronization is split. There's an arrive at the bearer and then there's a wait at that bearer. When threads are cooperatively executing, all threads continue to arrive and wait at the barrier. However, between the arrive and wait, each thread can schedule thread-independent work. So instead of being idle, waiting for other threads to arrive, each thread can be busy doing useful work. In the producer-consumer model, all threads operate in a decoupled manner. After the producer produces the first batch of data, it arrives and immediately starts producing the second batch of data. For the consumer, the data needs is available, it immediately starts to consume the data without any unnecessary synchronization. As you can see, an asynchronous design approach can lead to much more efficient parallel execution. Before I dive into the details of Hopper improvements, let's start with a review of the asynchronous barriers that were available in A100. Consider again the example where a set of threads are cooperatively executing on a set of data. As shown on the right, A100 synchronization barriers split the synchronization process in two steps. First, thread signal arrive when they are done producing their portion of the shared data. This arrive is non-blocking, so threads are free to execute other independent work. Eventually, the threads need the data produced by all the other threads. At this point, they do a wait, which blocks them until every thread is signal arrive. As showed before, the advantage of asynchronous barriers is they allow the threads that arrive early to execute independent work instead of waiting. Now, new for H100 is the ability for waiting threads to sleep until all of the threads arrive. On previous chips, waiting threads would spin on the barrier object in shared memory. Also new for Hopper is a new form of barrier called the asynchronous transaction barrier. The asynchronous transaction barrier is also a split barrier, but instead of just counting thread arrivals, it also counts memory transactions. There are new commands for writing memory that passes both the data to be written plus a barrier update. In fact, the barrier can be configured to track not only threads, but asynchronous memory transactions as well. The transaction barrier will block threads at the wait command until all producer threads have arrived and all asynchronous memory transactions have completed. This barrier is a very powerful new primitive, and it works great for asynchronous memory copies or data exchanges. Let's look how this new barrier support combined with block clusters improve block-to-block data exchange. On the left, you see how block-to-block data exchanges are done on existing GPUs. Data is exchanged to global memory using a barrier stored in global memory. The sequence for the producer is to write the data, do a memory barrier, write the barrier flag. The sequence for consumers to pull the flag to determine if the barrier is cleared and then to read the data. To perform this data exchange requires 3 to 4 round trips through global memory. On the right, you see how things are done on Hopper. Here you see the producer stores data directly into the consumer shared memory while updating a barrier that's also in the consumer shared memory. This enables a minimum latency data transfer of a one-way trip from the producer to the consumer and results in a 7x latency reduction. Hopper also accelerates memory copies using its new TMA unit. The TMA unit is able to do asynchronous memory copies between global and shared memory, as well as shared memory to shared memory copies between blocks in a cluster. Using the new memory transaction barrier, it can do copies with minimal latency. The TMA is fully asynchronous with thread execution. There is no address generation or data movement and synchronization management overhead required of the thread. From the thread's perspective, it is simply fire and forget. This makes for a simplified and efficient programming model. Here's an example of how the Halo data exchange is performed in Hopper with its new capabilities. Here we have a cluster of 4 thread blocks, each working on a different part of the data. When one thread block needs to get halo data from other thread blocks, the other thread blocks write it directly into its shared memory, updating a local barrier indicating the data is ready. Halo data exchange is efficiently done asynchronously with minimal latency. To summarize, the goal of asynchronous execution is to keep all units in the GPU fully utilized by allowing more overlap in computation and data movement. Hopper introduces an asynchronous transaction barrier for atomic memory movements and synchronizations and makes waiting on barriers more efficient. Hopper also introduces on-chip acceleration of memory copies called TMA. It frees general-purpose threads from doing memory operations and address calculations, allowing the threads to instead focus on independent processing tasks. Combining Hopper's improvements for locality and asynchronous execution and data movement, you get dramatic performance improvements. On the right, you see performance improvements on Hopper when those new capabilities are used. Taking advantage of locality and asynchrony provides 2 to 3x performance benefits on these key algorithms. Now let's look at some of the improvements Hopper has made to accelerate deep learning. At the heart of the Hopper SM is the new 4th generation Tensor Core. It has double the throughput per SM for all data formats. The Hopper Tensor Cores has also added support for a new 8-bit floating point format. It provides twice the throughput of FP16 and bfloat16 formats, matching the throughput of 8-bit integer. In order to keep these Tensor Cores fed and keep the GPU power in check, Hopper's Tensor Cores have improved operand delivery efficiency by 30%. H100, like A100, also supports sparse tensor arithmetic, enabling 2x throughput when the data is sparse. This chart shows the cumulative compute improvements from A100 to H100. The increase in number of SMs provides a 22% increase. The 4th generation Tensor Cores provide an additional 2x improvement. Switching from 16-bit floating point to new FP8 format provides an additional 2x improvement. Finally, clock frequency provides another 30% increase. All combined, Hopper provides 6x throughput increase over our previous generation. Let's look at the new FP8 support in a little more detail. On the left, we see the exponent range and mantissa precision provided by each Tensor Core floating point formats. You'll note that the Tensor Core supports 2 FP8 formats. One provides an extra bit of exponent range and matches the exponent range of FP16s. It can be thought of as a truncated mantissa version of FP16, like how bfloat16 is a truncated mantissa version of FP32. The other FP8 format trades off 1 bit of range for an additional 1 bit of precision. On the right, we see how the Tensor Cores process FP8 data. The multiplication of FP8 data can be accumulated into either FP32 or FP16. Once the matrix multiply is done, various common neural network functions, like adding bias or applying an activation function, can be performed at a higher FP32 or FP16 precision. The final result is then converted to desired output format before being stored back to memory. The graph on the left shows the numerical distributions for a variety of network layers in a single language model. You can see that the distribution can vary significantly. Some have wider exponent range and are best mapped to the E5M2 FP8 format. Others have a narrow exponent range and require more precision to differentiate between values. These are best mapped to E4M3 FP8 format. On the right, you see that during linear math computation, the range of the results can be outside the FP8 representable range. By performing the matrix multiply accumulation in the FP16 or FP32 formats, we are able to safely perform the computation without loss. But when converting to the FP8 format, we scale the results into the FP8 representable range. So while this new FP8 format can be used for both AI training and inference, how to use it? For this, Hopper's Tensor Cores are accompanied by a new technology called the Transformer Engine. The Transformer Engine manages the use of FP8 to accelerate the world's most compute-intensive models, transformers. This engine operates transparently underneath the deep learning frameworks and can be enabled or disabled with a simple toggle. Under the hood, transformers are simply graphs of compute-intensive layers. At each layer, Transformer Engine analyzes statistics and outputs values produced by the Tensor Core. From these statistics, it then infers what range is required to represent the tensor values. With this information and knowledge about which type of neural network layer comes next and what precision it requires, Transformer Engine decides which target format to convert the tensor to before storing it to memory. With FP8 specifically, the representable number range is limited to only a few bits. To optimally use the available range, the transformer engine is also dynamically scales tensor data into the representable range using scaling factors computed from the tensor statistics. In this way, every layer in the model operates exactly the precision it needs and is accelerated in an optimal way. Let me show you how the training and inference with FP8 works in practice. This slide shows how successful the transformer engine is able to train models using the FP8 format. In the table on the left, we see that it's able to use the FP8 format with negligible difference in accuracy. The graph on the right shows the training error over time for FP8 versus native BF16 or FP16. You can see that it very closely matches. I've already talked about how the new TMA unit efficiently performs asynchronous copies, but it was designed specifically to handle the complexities of copying and managing multi-dimensional deep learning tensors in memory. It will automatically compute the addresses, strides, and bounds checking needed for tensors up to rank 5. It will even automatically pad out of bounds values so you don't get junk when copies go out of bounds. All this is done with fire-forget model from a single thread. The Hopper GPU was designed with the rest of the system in mind, with direct support for tight integration with other system components and the ability to scale up and out. I'll give you a little bit of a preview of some of the integration and scaling capabilities of the Hopper GPU. You'll find a lot more details in upcoming Hot Chips talks. H100 is the heart of an accelerated data center. The H100 was co-designed with many innovations in the rest of the system to provide unprecedented data center scale performance. With Hopper, we are introducing a next-generation CPU cluster, the DGX H100 SuperPod. This new SuperPod is updated with next-generation GPUs, CPUs, and interconnects. A single 256 GPU SuperPod delivers over 1 exaflop of AI computing throughput. And it scales even further. Multiple of these SuperPods can be assembled into even large machines with many thousands of GPUs. I encourage you to check out the NVSwitch and SuperPod Hot Chip talk for more details. We've also developed the Grace CPU that was designed with the H100 GPU to be tightly integrated into a new SXM module. Grace Hopper introduces a new hardware coherent CPU-GPU interconnect, provides 900 gigabytes per second total bandwidth, over 7 times as much bandwidth of the new and already fast PCIe Gen 5 interconnect. With this much bandwidth, the GPU can access the CPU's large memory effectively as an extension of its own memory, thereby vastly increasing the total memory capacity available to GPU accelerated applications. I encourage you to check out the Grace CPU Hot Chip talk for more details. Now let's wrap up. The H100 GPU delivers a generational leap in performance, efficiency, and security. I hope you enjoyed a look at some of the technology details and features behind the Hopper H100 GPU. For more information, see the H100 white paper at the link shown below. I'd like to point out that H100 is the result of the hard work of many engineers at NVIDIA. I'd like to acknowledge and thank them for making H100 and this presentation possible. Thank you for listening, and I look forward to your questions.
Thank you, Jack, for a wonderful talk. Now let's look at some questions which have been submitted through Slack. So as previously mentioned by Cliff, please upvote the questions which you want to be answered live. So I will now go through Slack and ask Jack questions with the most upvotes. And Jack will stay till the end of the conference to address some questions which we won't be able to answer live today. So the first question is from Jeff Smith at Citadel Securities. Is the newly exposed SM network functionality added on existing L2 GPC buses or new connectivity altogether? And how does SM traffic scale with the same count?
It's a combination. I can't go into the microarchitecture details, but you can get the full throughput of the L2 cache while doing SM to SM traffic at full throughput as well. And the cross-sectional bandwidth of the SM to SM network is built more like a crossbar where you can get the full throughput of the SM to SM traffic as well. And it will scale, the cross-sectional bandwidth will scale with the number of SMs.
So the next question is from Nadine Jibara from Imperial College London. It seems most architectural improvements described are geared to leveraging more parallelism. Can you please shed light on the features that improve sparse arithmetic performance?
I'm not sure. It seems like two separate questions. I'll answer the first question first. Yes, it's designed to extract and manage as much parallelism as possible, to avoid serialization, avoid weighting as much as possible, so that you can make as much progress as possible as you can by extracting any amount of parallelism you have. The GPUs have been designed historically to take advantage of massive amounts of parallelism. But in this generation, we attempted to try to extract even more parallelism than you would typically find or naturally find from the design, make it easier to do so. As far as sparsity support, we do have a sparse matrix multiply where one of the operands is sparse. That was disclosed in Ampere, and the Hopper architecture continues to support that sparse matrix multiply support.
But just to be clear, there are no novel features in Hopper related to sparsity. It's essentially similar.
It's similar in terms of the matrix multiply, yes.
Thank you. Okay, the next question is from Aditya Yanamandra from Intel. Is the CM-to-CM network limited to 4 CMs physically, as shown in the foils, or does it scale in the way to 16 CMs within a GPC?
I'm sorry, can you repeat the question? I didn't quite...
Is the CM-to-CM network limited to 4 CMs physically, or can it scale further to 16?
You're talking about the SM-to-SM network that scales 16? 16 SMs is what I talked about?
Yeah.
Yes. In this architecture generation, it scales to 16, and you can have a thread block cluster that's up to 16 thread blocks. And that is the maximum scalability at this point.
Thank you. So the next question is from Thaddeus Fortenberry, TenStorrent. Have performance numbers been released on confidential features? What's the impact of secure versus clear?
We haven't released anything publicly. I think we released things to our customers, and I can't comment exactly what the performance characteristics are in detail.
The performance estimates which you've shared are just estimates, essentially.
Yes.
Thank you.
At least what's being described is the estimate, yes. More details require more NDA.
Okay, we have a couple of more minutes for a couple more questions. So the next question is from Charlie Demirjan from Semi-Accurate. What is the TDP range the H100 is meant to operate at?
I'm not sure what's been publicly disclosed, so I'm not sure I can answer that question. It's in the Slack. I will try to confirm what I can say and what I can't say and answer there.
Thank you, Jack. So maybe the last question from Ralph Wittig from AMD. So is the transformer engine fully implemented in hardware, or is there an algorithm that determines the scaling and precision selection, a combination of software and hardware? And if
the transformer engine is a combination of hardware and software.
And it's essentially...
It is not pure hardware.
Can it be upgraded through software?
Yes.
Thank you. So I know we haven't answered all the questions. Jack, if you could please join Slack and check and answer the questions and follow up there.
All right, I'll do so. Thank you. Thank you for the questions.
Let's thank Jack for the talk. I will clap for everyone. Okay, the next talk in this session will be given by Alan Smith and Norm James from AMD. They will be talking about AMD Instinct MI200 series accelerator and node architectures. The first part of the talk will be dedicated to SoC design and architect and will be given by Alan Smith. Alan is an AMD Senior Fellow, where he has led multiple generations of Instinct SoC architecture and performance. He has previously been an architect for AMD's Infinity Fabric and integrated North Bridge. Alan holds a master's degree in electrical and computer engineering and a bachelor's degree in electrical engineering from the Georgia Institute of Technology. And after Alan, Norm will pick up the talk and tell us about node and the system design. Norm joined AMD in 2019 after a long career with IBM as a system architect and lead engineer. He is currently the lead engineer and system architect for the Datacenter GPU business unit, where he works on the AMD Instinct GPU line targeted for HPC and machine learning. His experience spans circuit design, silicon manufacturing, system architecture and design, firmware development, and software development. Let's welcome Alan and Norm, and let's hear about the new AMD GPU.
Thank you, Natalia. We're excited to be here today live and in studio on behalf of the many AMDers who worked on this program to discuss the AMD Instinct MI200 series accelerator and node architectures. Over the past 25 years, leadership class supercomputer performance has been growing at a rate of roughly 2x every 1.2 years. This rate is much faster than Moore's law, which implies innovation beyond what can be enabled with silicon scaling alone. It requires advances in architecture and design at the chip and system levels to enable higher density, efficiency, and scalability. The demand for these systems is not simply driven by top 500 bragging rights, but to solve humanity's grand challenges around medicine, climate, energy, and many other areas across various scientific disciplines using traditional simulation and increasingly AI for science. At AMD, we believe in the importance of these endeavors and are excited to have launched the AMD Instinct MI200 series accelerators last year, now deployed at scale in the US Department of Energy Frontier supercomputer and other leadership class machines in Europe. In today's talk, Norm and I will be covering the many innovations of the AMD Instinct MI200 series and some of the motivations that led us to these design points. I'll start with a walkthrough of the multi-chip accelerator module and how we enabled massive generational scaling of compute throughput and memory performance. I'll then cover the key elements of the CDNA2 architecture that enabled MI250X to be selected by Oak Ridge National Laboratory for Frontier, exceeding the target of 1 exaflop running high-performance LinPack under the 30 megawatt total system power budget. Finally, I'll discuss the third generation AMD Infinity architecture that provides a flat coherent memory space across the node and is optimized for network scale-out with the mindset of the accelerator as the first-class compute and memory element, enabling simplified programming model, especially for codes being ported to the accelerator from the CPU. Norm will continue the discussion with an overview of the Frontier node and other topologies and systems made possible with the MI200 series. The scaling of MI250X begins with the compute unit, with wider data paths for single, double, and mixed precision floating point math. Each of the two GPU-derived accelerator dies, known as graphics compute dies, contain 110 active compute units organized in 8 shader engines. These shader engines are arranged around a central L2 cache per die. The L2 is organized into slices, which are connected to the HBM2E memory system, as well as the AMD Infinity Fabric that interconnects the two dies and the high-speed SerDes for off-package Infinity Fabric and PCI Express. The aggregate memory capacity of 128 gigabytes and bandwidth of 3.2 terabytes per second are optimized for memory-bound HPC workloads. Flexible, high-speed I/O allow MI250X to connect to optimized third-generation AMD EPYC CPUs and scale up to 3 additional MI250X modules per node. The integrated PCI Express root complex enables a network interface card to be directly connected to the accelerator. Together, these features allow for maximum scale per module and high-performance scaling at the node and system level, enabling exascale-class supercomputers. The module described in the previous slide is made possible through AMD's advanced packaging and integration leadership. 2 CDNA2 dies and 8 stacks of HBM2E memory for a total of 10 chips are interconnected using technologies optimized for the individual requirements of each element. Elevated fan-out bridge provides the density required for terabytes of bandwidth between the HBM stacks and the compute dies, while high-speed Infinity Fabric is connected through the package substrate. This solution has proven robust and manufacturable, allowing AMD to deploy MI250X reliably at exascale. AMD has spoken in the past on our approach to domain-specific architectures. There is a continuum of potential architectures, starting with the general-purpose CPU, easy to program with vast amounts of software out there running on it. CPUs are not going away for these reasons, but their energy efficiency is limited. From there, we move into the accelerator domain, and in this talk, we'll focus on GPU-based accelerators. As we know, many codes can take advantage of GPU accelerators. They are good for dense math calculation in domains like high-performance computing, machine learning, and obviously for processing pixels. To get even more efficient, we can become even more specialized. AMD has taken this route with the bifurcation of our GPU line into CDNA for compute and RDNA for gaming. Our CDNA line doesn't need the 3D shading and pixel processing hardware of our gaming line, and therefore can dedicate more energy and area to computation. This makes it more efficient for those applications. This sort of domain-specific approach yields significant benefits. The CDNA2 compute unit features domain-specific architecture innovations that I'll expand on in the following slides. In addition to architecture, we applied AMD's decades of CPU experience and expertise optimizing logic and implementation for high frequency to increase MI200's frequency capability without increasing power. What this did for us is not only enable higher maximum performance, but also improve performance per watt. As is well known, power goes with voltage squared. By operating at a lower voltage at the same frequency, we were able to optimize performance and energy efficiency. We also adopted low skew and power-efficient CPU clock distribution approaches, while dramatically improving our clock gating efficiency to only toggle gates and flops when they're doing useful work. The net benefit of these and other optimizations is a 2x improvement between MI100 and MI250X in delivered double precision gem flops per compute unit at the same power. The CDNA2 compute unit is the heart of MI250X, and as I mentioned earlier, is the foundational element of scaling the design. We started by widening the double precision vector data path and added additional double precision capabilities to the matrix cores. New instructions were added to optimize accumulator data forwarding and reuse. The matrix core accumulators and general purpose vector register SRAMs were combined, providing flexible storage to maximize latency hiding for all types of workloads. These changes combined to provide substantial reductions in power and 4x the previous generation's double precision matrix throughput, as well as doubling the previous generation's double precision vector throughput. This enables record-setting HPL and substantial uplift across broad classes of HPC applications. However, we didn't stop there. These new data paths were utilized to add new packed single precision floating point instructions for commonly used operations to provide 2x throughput over standard FP32 ops. These capabilities are optimized for computationally dense FP32 kernels that cannot leverage the matrix cores. We've seen particular success using packed FP32 in in-body problems such as HAC, GROMACS, and LAMPS. Finally, throughput of BrainFloat 16 was doubled to match the throughput of IEEE's 16-bit floating point, giving data scientists flexibility to use either format without compromise in performance. To match the scaling of the compute unit throughput and to enable large working sets, MI250X was built around HBM2E. Each compute die has 4 stacks of HBM, and the 2 dies are interconnected with 400 gigabytes per second of bidirectional bandwidth Infinity Fabric. The Infinity Fabric network on chip was enhanced to 64 bytes per clock per channel to meet the external and module interconnect demands, as well as enable efficient arbitration and operating voltage while delivering maximum HBM bandwidth. The memory system and accelerator L2 cache are organized in 32 physically partitioned slices per die. Each of the L2 slices provides 128 bytes per clock, delivering 2x amplification and bandwidth versus the memory at the same frequency. These 32 slices are interconnected to the 110 compute units, delivering the bandwidth needed to feed the math. The L2 arbitration architecture was optimized to increase efficiency across varying compute unit load. We also added 64-bit floating point atomic operations to each L2 slice. This allows many parallel threads to reduce data into output values without the need for separate reduction kernels or complex parallel reduction algorithms, and provides high performance even with moderate contention. All of these enhancements and optimizations come together with a roughly 1.7x increase in the total number of compute units per module enabled by the 2-die multi-chip construction and scaled power of the MI250X to deliver between 2x and 8x uplift in peak performance across numerical formats when compared to MI100. In addition, HBM2E memory systems provides an increase in peak theoretical memory bandwidth of 2.7x and quadruples the memory capacity between the MI250X and MI100 modules. The third generation AMD Infinity architecture brings together multiple MI250X modules and the EPYC CPU into a unified shared memory node. This allows programmers to have fewer explicit and redundant memory allocations and fewer explicit memory migrations. As a result, it is easier to migrate existing CPU-only codes to the accelerator. And since you can coherently cache GPU HBM from the CPU, you can operate CPU codes out of GPU memory at high performance, eliminating the need for constant copies back into the host memory. Full accelerator hardware coherence of local HBM memory means you can avoid cache invalidation operations at kernel start points, which can result in higher performance for small kernels. Finally, the PCI Express fabric is extended into the MI250X module, allowing the 200 gig NIC to be directly connected to each accelerator with sufficient bandwidth to sustain line rate, enabling efficient network scale-out across thousands of nodes. I'd now like to turn the presentation over to my colleague Norm James to discuss MI200 series node topologies and systems.
Thanks, Alan. I'll start with the flagship MI250X HPC topology used in the Frontier supercomputer. HPC demands high bandwidth between the GPUs and from the GPU to the scale-out networking for MPI communication. This topology meets the requirements through 5 GPU to GPU Infinity Fabric connections for each GCD at 25 gigabits per second and a total fabric bandwidth of 1.54 terabytes per second. For scale-out bandwidth needs, we have a 25 gigabit per second extended speed mode PCIe connection to a 200 gigabit network adapter. ESM allows for higher than standard PCIe data rates and is perfect for applications demanding high bandwidth, such as HPC. This topology also utilizes an optimized AMD EPYC CPU that feature Infinity Fabric between the CPU and GPU, which enables the unified memory model with all the benefits highlighted by Alan on the prior slide. The flagship HPC topology is implemented in the HP Cray EX235A blade, which is the primary building block of the Frontier supercomputer. Each blade has 2 nodes with liquid cooling and ultra-dense packaging. Each node contains 4 MI250X, 1 GPUs, 1 EPYC CPU, 2 Slingshot network mezzanine cards with 2 ports each, and a storage mezzanine card. In the picture, you can see the 4 OEM cold plates and 2 network mezzanine cards for each node. The CPU resides underneath the storage adapter on the right-hand side. Frontier is organized as 8 blades in a chassis and 8 chassis in a cabinet for a total of 128 nodes in a cabinet. Many thanks to HPE for an extraordinary system design using AMD technologies. MI250X's peak FP64 performance of 47.9 teraflops, peak memory bandwidth of 3.2 terabytes per second, packaged in the HPE ultra-dense blade, led to a historical milestone of exceeding an exaflop, 1.102 exaflops to be exact. Not only did Frontier in this design secure the #1 spot on the top 500 supercomputer list, the same design also secured the #3 spot. To give some context to this level of performance at 1.102 exaflops, Frontier is more flops than the next 7 supercomputers combined. That's right, combined. With this level of performance, we met the needs for the scientific community to solve the compute-intensive problems for the advancement of our society. Exceeding the exaflop is no doubt an extraordinary achievement, but in today's world, power consumption and power performance are at least as important metrics. One of the ways we achieve this feat is through the domain-specific optimization of the architecture to focus purely on computation without the overhead of 3D shading and pixel processing, as required by traditional GPUs. These domain-specific optimizations, combined with the relentless focus on power efficiency from the transistor all the way to the platform level, enabled the MI250X-based designs to capture the top 4 spots on the Green 500 list. At 62 gigaflops per watt, Frontier is 1.5x higher performance per watt than the next best supercomputer using other vendors' silicon. So not only is Frontier the world's fastest supercomputer, it is also the world's most power efficient. A crowning achievement in today's energy-conscious and constrained environments and a top focus for AMD. In addition to the HPC-focused topology, this topology is targeted towards mainstream 2-socket accelerated servers. It has the same GPU to GPU bandwidth as the flagship HPC topology, but is designed to be compatible with general-purpose CPUs that support PCIe Gen 4. Notice each GCD has a by16 connection, so even though there are 4 MI250 OAMs, there are 8 by 16 PCIe connections, twice as many as comparable solutions. The connection between the CPU to GPU is generally through a switch to provide optimal RDMA access to the networking and storage adapters, which is also attached to the switch. Overall, this topology combines the bandwidth to meet the needs of an HPC applications with the flexibility to be integrated in a variety of platforms. This is our power-optimized glueless topology for machine learning. Not only does this ML topology have twice as many GPUs as the HPC topology, but it also has 1.5x the ring bandwidth. There were not enough I/O to fully connect 16 GPUs, so this topology optimizes the ring bandwidth for best performance with the AMD ROCm Communication Collectives library, which is essential for training workloads. Frontier is truly awesome to use with all that compute power at your fingertips, but it's not accessible to everyone. So I also wanted to show you some generally available MI250 servers. The Gigabyte G262Z00 server also uses 4 MI250 GPUs and the mainstream topology connecting to dual EPYC CPUs, AMD EPYC CPUs. It has 4 2.5-inch drive bays, 6 low-profile Gen 4 slots, 1 OCP mezzanine slot, and the 2U height enables optimal density for an air-cooled solution. In addition to the Gigabyte server, the Supermicro AS4124GQ server, which also uses 4 MI250 GPUs connected using the mainstream topology, is in a 4U server. This server has dual AMD EPYC CPUs, 32 DDR4 DIMMs for a total memory capacity of 8 terabytes. The Supermicro server has 10 hot swap 2.5-inch drive bays and 8 PCIe slots. So in conclusion, we have shown you the industry-leading capability of the MI200 series products and how they are incorporated at the system level, all the way from the 2U servers all the way up to supercomputers. It is essential to the scientific advancements that AMD delivers high-performance computing and optimal power efficiency, and we have done just that. This power efficiency is through an optimized architecture focused on critical workloads, which needs the ultra-high memory bandwidth delivered by 8 stacks of HBM2E memory. The unified shared memory enables a simplified programming model and allows for more time to be spent solving the complex problems. All of this has culminated into the world's fastest and most power-efficient supercomputer, powered by AMD Instinct MI250X GPU. Thanks to all the AMD engineers from multiple business units that turned the MI200 product family into a reality. And thank you to HP and Oak Ridge National Labs for delivering and productizing a world-class supercomputer. Finally, thank you to everyone watching, and we hope you get a chance to use an AMD Instinct MI250-based computer. Thanks.
Thank you, Alan and Norm. Now let's get to some questions. So in Slack channel, by far, I think the most upvoted question is not about hardware, it's about software. So the question is, can you comment on the software ecosystem for deep learning that runs on top of MI250X? And what should we do to be able to run TensorFlow, PyTorch, JAX seamlessly on that one?
Well, okay. So you got a couple of hardware guys here to try to answer the software question, but I'll do my best. And we'll follow up on Slack with more details. But the ROCm ecosystem has been advancing as we've been moving through the first and now second generation of Instinct processors. And I think just recently ROCm 5 was released. We also have been working to upstream the Instinct compatibility into TensorFlow and PyTorch. So it's a work in progress.
And I think I've even seen announcements that DeepSpeed now runs on top of ROCm. Is it true?
Right.
Yeah.
Recent announcements and partnerships with Microsoft and DeepSpeed on bringing ROCm compatibility.
That's actually really cool.
Yeah.
Okay, two other questions. I will bundle them together because I think they're related. So why does MI250X show up as 2 different GPUs to software instead of as one like the Apple M1 Max? And why did you design the GPUs as such? And the first part. And the second, are there any applications or any workloads for which ROCm can view the 2 die as a single GPU?
Okay, that's a good question. I can answer that one. Okay, so right, so you saw in the diagrams that the MI250X is designed as a 2-chip multi-chip module, a 2-die multi-chip module. This was really a first generation in bringing that much memory bandwidth and capacity into a single module. And there were limitations that we had in the implementation in terms of how much bandwidth we could deploy between the two dies in the socket. And so we made a decision that we would present each of the chips independently as a separate GPU, and that they would run as a separate MPI rank or a separate guest. And this was really related to the bandwidth that, just comes back to the bandwidth. The fact that we couldn't match the HBM bandwidth between the two dies means that the two dies need to be treated somewhat special relative to each other. So we present them as a single device. As two independent devices. It is possible to take advantage of the memory bandwidth that's in the socket or within the module relative to the external bandwidth to share some data structures that are useful, within the module. And so we have some examples of how people are doing that as well. Hopefully that gets to the question.
Thank you. Then there is a follow-up question also from George Cosma, Chips and Cheese. What's the register size, file, and bandwidth per compute unit?
I know, but I'm not sure it's right for this generation, so I think it'd be better if we follow up on Slack with that one.
Thank you. Okay, probably we have time for one last question from Amarveer Chana, University of Cambridge. Why is the matrix FP64 throughput equal to the FP32 matrix throughput when the vector throughput is 1:2 ratio with backing?
Right. Yeah. That's just a design choice. The implementation of the double precision matrix engine is highly optimized for the mission of delivering the record-setting DGEM runs that we were targeting, and we wanted to make sure that we were optimizing everything that we could there. And so, like I talked about in the talk, we did take advantage of some of those same data path structures to implement single precision GEM and the single precision packed FP32 data types. But we chose not to increase the single precision GEM throughput.
Thank you. Let's thank Alan and Norm for a very interesting talk, and hopefully we'll have a chance to answer other questions on Slack. Okay. The next talk in this session will be given by Hong Jiang at Intel. Hong will be presenting to us Intel's Ponte Vecchio GPU, talking about architecture, system, and software for this new GPU. Hong Jiang is an Intel Fellow and the Director of GPU Computer Architecture at Intel Corporation. He currently leads the hardware research and development for GPU-based machine learning and data parallel computing. He is a 26-year veteran at Intel. In 2015, he was named an IEEE Fellow for Leadership in Parallel Multimedia Computing Architectures and Systems. He holds more than 120 issued and pending US patents and earned a PhD degree in electrical engineering from University of Illinois at Urbana-Champaign. Let's welcome Hong and hear about Intel's Ponte Vecchio GPU.
Hi, my name is Hong Jiang. I'm the Chief GPU Compute Architect at Intel. The title of my presentation today is Intel's Ponte Vecchio GPU, Architecture, Systems, and Software. Here is the agenda. First, I will provide an overview of the Ponte Vecchio platform, followed by the oneAPI software stack. Then I will go deep to talk about key architecture considerations that are important for achieving the performance targets. In the end, I will show some performance numbers for applications enabled through the oneAPI software stack. Ponte Vecchio GPU is a general compute accelerator based on Xe HPC architecture. In order to push the compute density, we are packing two compute stacks in a single package. We provide the flexibility for software to treat these two stacks Ponte Vecchio GPU as either 2 sub-devices or a single NUMA device. The two stacks have up to 128 Xe cores. Xe core is the basic compute unit that contains vector engines, Xe matrix extension, XMX matrix engines for AI, load store unit, and level 1 cache. There are 8 hardware contexts allowing concurrent execution of different application processes. For example, one application with 8 MPI ranks can map one MPI rank to each GPU context to allow them to run in parallel. We have 8 HBM2E memory controllers with a total of 128 GPU memory. There are 16 Xe links for GPU to GPU communication. Xe link provides point-to-point communication for a large number of Ponte Vecchio GPUs in a node without using a switch. Here, we are showing an illustration of how we can take Ponte Vecchio silicon and scale it up and build a system around it. We prototyped a 2-stack Ponte Vecchio GPU on the OEM. We then pair 4 of those on the 4 OEM subsystem. We then pair that with dual-socket Jiang Sapphire Rabbit host and with liquid cooling, prototype this in a 1U server node. Now let's transition to talk about the software stack, the one API software stack. For compute with accelerators, it's super critical to have the complete end-to-end software ecosystem. The idea behind one API is the layered abstraction. The intent is to have at the top level application, service, and solutions to be open, free, and everywhere. And we provide 2 levels of abstractions. Level 1 abstraction contains direct programming language, API programming library, and tools. From the blue color shows the library and language Intel provided to the ecosystem. For that, we have SQL and OpenMP language, and a set of one API libraries. Below level 1, we provide a level 0 abstraction, which really serves as a layer connecting level 1 and the target hardware. The hardware can be x86 ISA or ARM ISA, or Xe GPU or other vendors' GPU ISA. And this also expands to FPGA or ASICs. Now, let's talk about level 0 API. Level 0 API is a thin layer between the level 1 programming languages and performance libraries and the target hardware. It has 3 components: core API, tools API, and system API for system management. For the core API, it is critical to provide fine-grained controls and low latency services. We started with a multi-threaded design for performance scalability. The system API manages the hardware capabilities such as ECC, RAS, engines, and memory, and also hardware properties like power, frequency, and temperatures. For Ponte Vecchio GPU, level 0 API is simply part of the graphics driver. As I just mentioned, a set of tools are provided in level 1. Besides functional debug and performance profiling tools, here I highlight another one called Intel DPC++ compatibility tool. The intent of this tool is to ease the effort for developers to migrate their CUDA code to SQL. The migration is done once, and the tool generates human-readable code. Based on our experience, 90 to 95% of the code can be migrated automatically. Then developers can use the help of inline comments to finish porting the application. I will show some performance examples later. Recently, Intel has released the open source version of this tool under the project name called Choquette. Now let's talk about the Ponte Vecchio architecture ingredients. And let's start with throughput. Ponte Vecchio packs a lot of compute in the package. And in this table, we show the vector and the matrix computation throughput. It's important to have high throughput 64-bit floating point operation for HPC. That's the market we care about. So we pack 2x throughput of 64-bit floating point compared to the traditional implementation. So you can see in the table, the throughput of double precision 64-bit floating point is the same as single precision floating point throughput for vector. And the later part of the table shows the matrix operation throughput. And we support very common data format like bflow16 and TF32 throughput, which is half of the bflow16 throughput. And for AI inference, we also provide int8 data format support as well. In order for us to sustain such high throughput, it's very important to have the memory hierarchy to bring the data close to the compute. And in this table, we have register file, L1 cache, L2 cache, and memory. And you can see that we put large number of storage close to compute, which is register file and L1 cache. 64 megabyte register file and 64 megabyte L1 cache. And in addition to the L1 and register file, we put very large L2 cache, 408. We also put very large L2 cache, over 400 megabyte size. Right? That really helps us to keep data on die instead of have to go out to the HBM memory. That's just a set of the cache. We also have to provide layers of throughput. In this table, it shows the ratio of 4-to-1 ratio between the register file to L1 cache, 8-to-1 ratio from L1 to L2, and 4-to-1 ratio from L2 to HBM. And one unique feature of Ponte Vecchio is that we also build much bigger L1 per instance. L1 and register file are set part of the Xe core. And for each Xe core, there are 512 kilobytes of L1 and 512 kilobytes of register file together. That's a lot of application to block large amount of data in the Xe core to reduce the traffic to the remote L2 cache. So that's just the speed and feed. And we also built layers of other techniques to improve the compute efficiency. Let's go through that layer by layer. At the register file layer, we have both register caching, which is a microarchitecture feature that's transparent to the application to allow us to reduce the register access rate. And we also expose to the application the accumulator as additional register file that actually have a lower latency and also improve the total aggregated bandwidth of the register file space. For L1 and L2 cache, we built a different flavor of cache control, allow the application to control whether we use a read through, read back, or uncacheable control. In addition to the read back, read through, we also support a mode called read streaming. That means a final read of data does not perturb the residency of the other important data in the cache. So those are the cache control. So we also built a two-level of prefetch in the system. One is controlled by the software. The kernel instruction can issue a load operation that brings data into L2 or L1 without going to the register file directly. And we also have another way to control the state prefetch that at the front end of the GPU through the state prefetch either bring instruction into the cache or bring the application data into the cache. And here's an example to show the benefits of having a very large L2 cache. And this one example here is 2D FFT. And 2D FFT is notorious about the memory bandwidth because between the two 1D FFT operations, data has to be somewhere. Having a very large L2 in the hundreds megabyte range allows us to run FFT without really touching the HBM memory for the intermediate data. Here we have done some experiment using the Ponte Vecchio system. We configured the L2 at different sites from the total size of 400 megabyte to 80 megabyte or 32 megabyte to match with other GPU's sizing to see how effective this L2 cache is doing for this 2D FFT. You can see that more than 2x performance difference is observed for this one. Really brings memory bound workload into a cache and compute bound. And here's at the application level, for example, for DNN case here, for less than 50 training, we compare the sensitivity of application throughput due to the different sets of cache. You can see that the difference is more than 20% at the end-to-end application level. And early on, I mentioned that for the matrix operation, the throughput is much higher. In fact, the matrix operation throughput compared to single precision floating point is like 16x. And that really putting a lot of pressure into the memory hierarchy. And to reduce that pressure, we focus on operation offload. We built something called the transport data port as part of XC core. The transpose data port provides block load and store capability for data operations. That includes boundary condition check, zero padding the boundary, and also provide hardware transpose. Very important because when we deal with matrix operations, many times you perform A and B or A matrix, B matrix transpose. And those operations tend to require additional data operations in addition to compute. And we offload both address calculation and transpose operation from the compute unit. Combine that with latency coverage technique, large register, large L1 cache, and load loop unrolling, and also prefetch. We're able to sustain very high matrix operation throughput as shown in this chart. The bfloat16 gem, the matrix multiplication operation, can reach over 95% efficiency, compute efficiency for the machine. That's really difficult without all those operations offloading from the machine. Let's talk about another aspect of the architecture. Ponte Vecchio architecture support both SIMT operation mode and SIMD operation mode. The SIMT, single instruction, multiple thread, or single program, multiple data, I can exchange, is a similar concept here. It's a very common GPU programming model. And we support SQL and OpenMP programming environment for SIMT operation. And we also provide DPC++ compatibility to help people to migrate CUDA code into the SQL programming. We have both SIMT backend and also SIMD backend. So for SIMD, on the SIMD side, we support programming language, SQL eSIMD, and OpenMP SIMD. And for that, we support flexible SIMD widths, like 8, 16, and 32 SIMD widths. And this is a very common CPU programming model, and many HPC application has been written in this way. Easy transition of those HPC applications from CPU to the GPU. In this page, we show the effectiveness of our DPC++ compatibility tool. We start with some popular legacy CUDA workload and port it using this tool to SQL. And in this chart, you can see that running the SQL code on the competitor's hardware, NVIDIA's A100, have the similar performance as just original CUDA code. And the same code we are able to run on PVC as well. And the chart shows that the performance of PVC using the same SQL code base is able to deliver up to 2.5x performance over A100. Now talk about the SIMD code. And as mentioned earlier, PVC hardware support both SIMT backend and SIMD backend. And there are many OpenMP SIMD code written for CPU. And taking the same code, transition to PVC is much easier through the OpenMP SIMD 2-chain. And we can quickly achieve the performance target using that. The chart shows the same effort on the hack workload using SIMD backend or SIMT backend. We can see that the SIMD backend is able to achieve the performance earlier, while the effort on SIMT backend is still ongoing. First, talk about the SIMT and SIMD. Here's one example. When you have a certain part of the code that has high register pressure, we have a way to use explicit SIMD control through OpenMP to use narrow SIMD so that reduce the register pressure and get through that one. We sacrifice the parallelism for this part, but in the end, the application performance will be better. Now, that is the key architecture features we have in the system. We also talk about the software language support and one API application. Now we can see some application performance in the system. Now we show the application result of 3 HPC applications. Mini-build is one of the HPC applications for drug discovery. And we implement the application through Intel DPC++ one API. And in this picture, you can see that compared to NVIDIA's A100, Ponte Vecchio provides 2x performance lead. XSMR is the one major exascale project that contains multiple applications. And the NAC-RS is one of the applications. And we implement NAC-RS using Intel one API DPC++. And the performance chart on the right shows the key benchmark comparison between NVIDIA's A100 and the Ponte Vecchio. It's roughly 1.5x performance difference here we show. Next is OpenMC, which is another application. It's a Monte Carlo computation. And again, compared to NVIDIA's A100, Ponte Vecchio provides 2x performance lead. Here's a summary. We have shown today Ponte Vecchio has the largest high-speed cache in the GPU. We support open software model with the flexibility of SPMD and SIMD. And we deliver leadership performance. And finally, if you're interested in winning some cool prize, match my headshot to this logo, and you'll see on the slides. And you will enter to win either a NUC PC or other goodies.
Thank you, Hong, for a great talk. Now let's take a look at some questions in the Slack. I think we have enough time to answer maybe most of them. So the first question is from Ashutosh Dar, NVIDIA. Is the L1 8 megabyte cache shared split across 16 cores in the slides, or is it private for every core?
The L1 cache is private to each XE core. So for each instance, it's a 512 kilobyte. So 512 kilobyte L1 per XE core.
Thank you. So the next question is from Cliff Jiang, Google. The transpose data port, about transpose data port. Can you talk about sustained throughput, either per XE core or per 2-chiplet package?
I see. We designed the transpose data port as a read of L1 cache so that we can really bring the data from what's stored in L1 and to the register file. And as mentioned in the talk, we also have a prefetch capability to fetch data all the way from memory to L2 and L1. And so in typical use case we have in the implementation, we bring data to L1 first. Then the transport data port is able to quickly bring the data from L1 to the register file. So in the order of L1 cache throughput.
Thank you. The next question is from Anirban Ghosh. Is the L2 cache the same as the Rambo cache described before?
Yes, Rambo cache describes a construction of Ponte Vecchio, and we demonstrated previously that Ponte Vecchio is a 3D stacking technology, and some of the tile on top of the base tile are SRAM tiles, and those are named as Rainbow Cache. So Rainbow Cache really expands the footprint of L2 memory. Therefore, we're able to pack 408 megabyte of L2 total footprint in a single package.
Thank you. The next question is from Tom Gooding, IBM. What is the stack-to-stack bandwidth? Can an XE core on stack 0 directly address memory of stack 1 HBM controllers?
Okay, I don't recall the precise number, but the answer is yes. The memory coherent across the two stacks, so that XE core in stack 0 is able to access the memory from stack 1. So, but the stack-to-stack bandwidth is not as fast as the HBM. So there is a NUMA effect in this operation. So when you carefully position the memory associated with the compute, you're able to get a very high throughput. But if the memory position is not precise, so that may be a performance bottleneck. So we are in the process to provide a software structure to enable such a NUMA programming in these devices, so that the application that is NUMA friendly can get very nice performance while using the full 128 megabyte footprint available for in single package, right? So that's really nice. But if you are really high throughput operation that have a good locality, and the two stack can also be configured as two sub-devices and independent to each other. So both ways are supported.
Thank you. Let's take the next question from Alfredo Lima, Alpha Tech Lab. The question is about difference in performance numbers reported last year versus this year. So he mentioned that if P32 throughput was 45 teraflops and now last year, and now it is 52 teraflops. He asks where the difference comes from. Is it due to frequency increase, power consumption, both?
Yes. So, yeah. So last year we showed the demonstrated performance of single precision at the 45 teraflops. And in this presentation, I showed a spec performance at 1.6 gigahertz. So if you calculate a flop per cycle and 1.6 gigahertz, that's the number come over here. So we just want to be consistent in this presentation. We use the spec numbers.
Thank you. So let's take the next one from Keelan Cavalotti, Stanford. What's the TDP of a single Ponte Vecchio OEM module? Okay,
the OEM module for Ponte Vecchio is 600 watt. It is the module power, including the motherboard power loss from the power supply all the way to the socket. So the total power of the board of the module is 600 watt.
Thank you. So the next one from Justin Emerson, Pure Storage. What explains the performance increase when going from native CUDA on A100 to SQL?
We are still in the process to understand all the details. Some of the performance increase is just code efficiency, and the chart really shows the SQL as a language is pretty effective to express the problem that was written in the SIMT fashion that was in CUDA, right? So the language is pretty efficient, and also the developer has the freedom to do performance tuning using this SQL language. So therefore, depending on the effort you put in there, sometimes you push harder, you get higher performance. But in general, having the performance on par with CUDA really illustrates the foundational efficiency of the language.
Thank you. And there is a slightly related question from Mark Grossman at Microsoft. Can you also share any comparison for perf per watt for CUDA versus writing SQL code on?
We just run the code out of box, so the performance should reflect the performance per watt. We did not change the system configuration, just run the CUDA code on A100 and run the converted SQL code in the same machine and report the numbers. So there's no specific power changes. Therefore, performance number should reflect the performance per watt.
Okay. Thank you. I'll use an opportunity being a chair and also ask a question from myself.
Okay.
So you showed some interesting increase in performance due to increased size of L2 cache. Have you modeled if you increase the L2 cache even further beyond 408 megabytes, how that will impact the performance of those applications?
We did analysis of the sensitivity across the board, mostly in simulation, because once we have a silicon, we're able to reduce the size of the cache to see how big a cache help compared to a smaller cache. In the simulation environment, we did run all the way through to the much bigger size and identify where are the next cliff of performance. Really, if you think about the typical workload size of the cache, they try to track the current workload, current working set of data. When the cache is in the megabyte range, now you're talking about data across the working set. For AI, it's simple. Between layers, the data may be resident in the L2 cache instead of pushing out to HBM. But the next level would be more deeper in the layers, more bigger set of workload. So we see that the next cliff, if a new technology coming on board, we are studying a new technology in this space to see what are the next cliff we can further push the compute efficiency with a different memory technology.
Okay, and I suspect that results for example, ResNet 50 benchmark was on like standard. Was it on standard ImageNet images?
That's right. We run the.
So if I push the size of the images to larger sizes from like standard ImageNet images, then
that may be a factor in there for sure. It's really the working set of data, right? So and the batch size also factor. Right? If you run bigger batch, then you consume more footprint. So it's a trade-off, and we actually see an interesting behavior of the workload because batch size is one factor to see how much compute density you can pack in the machine. And when you increase batch size, it's better in terms of flop per byte ratio. But when you increase too much, you start trashing the cache, then there's a nice curve you can draw, and where's the sweet spot in that curve.
Thank you. So there are a couple more questions on the Slack, and I think we can answer probably one or two.
Okay.
Can you comment on planned scale-out topologies? That's a question from Ashutosh Dart, NVIDIA. Can your coherency domain be larger than 8 GPUs?
Sorry, can you repeat the question?
Yeah. Can you comment on the planned scale-out topologies, and can your coherency domain be larger than 8 GPUs?
Okay. Within a node, within a compute node, for example, with 2 Sapphire Rapids Jiang core, we can put, say, 8 Ponte Vecchio GPU with XC-link connection so that there will be connected point-to-point directly for up to 8 GPU with no shortage of link. We have 8 links. You can only use, we use 7 of the 8 link pairs. And that's for the scale up. For scale out, we use a traditional NIC connection to connect the node to node.
Thank you. Thank you, Hong, for a really good talk and for answering all the questions. Please check the Slack. There are a few other unanswered, so I'll leave it to you to answer them on Slack.
Thank you very much.
Okay, so we've heard from NVIDIA, AMD, and Intel about their novel GPUs architectures. Now we have the last talk in the session from Biren Technology about their VR100 GPGPU. The talk will be given by Mike Hong and Lingjie. Mike Hong is the Chief Technology Officer of Biren Technology. For the past 28 years, Mike has been working on GPU architecture design and took Chief Principal Architect role in A3 NVIDIA and HiSilicon. Mike holds more than 60 US patents, including the block texture compression patents, which are the base for DXT17 texture compression formats in Microsoft Windows API. Mike received his bachelor in mathematics from Peking University and master's in management from Tsinghua University, and also master's in computer science from University of Buffalo. Lingjie is the co-founder and the president of Biren Technology, where he oversees product marketing and solution engineering. In the past decade, he held various management and architect roles in NVIDIA, AMD, and Samsung, and helped bring many GPU products to market. Before co-founding Biren, he was a director at Alibaba Cloud, responsible for its heterogeneous computing infrastructure for AI applications. Lingjie was an early advocate of MLPerf community and later became the founding board member of ML Commons. He holds a bachelor degree from Shanghai Jiang University and master degree from University of Technology at Austin and an MBA degree from Berkeley. So we'll hear first from Lingjie about high-level overview of the Biren GPU, and then Mike Hong will dive deeper into technical details. Welcome, Lingjie and Mike.
Hello, I'm Lingjie Xu, co-founder and head of product of Biren Technology. Biren designs high-performance accelerated computing chips for AI and graphics workloads, and provides end-to-end platform solutions. It is my honor to present our first-generation compute product, BR100. BR100 is dedicated to addressing the challenges of AI training and inference in data center, with ultimate goals of increasing productivity and reducing overall cost of ownership. As we call it a GPGPU, it is also capable of handling other general-purpose computing workloads as well. Let's take a look at BR100 spec. With 77 billion transistor count at 7 nanometer, the full implementation of BR100 delivers 2048 INT8 TOPS, 1024 BFlow16 T-flops, 512 TF32 plus T-flops, and 256 AP32 T-flops tensor performance, making it one of the fastest GPUs in the world. On the memory side, the chip is attached with 4 HBM2E stacks with up to 64 GB memory capacity. Together with 8 scale-out Blink interconnections, BR100 can provide over 2.3 terabytes per second aggregated external I/O bandwidth. With such strong raw horsepower, let's also take a look how BR100 performs on real-life workloads. Compared with NVIDIA A100, at the current stage, we see an average of 2.6 speedup over a broad range of benchmarks across different domains, including computer vision, natural language processing, and conversational AI. Performance will continue to go up in the coming months as we keep optimizing hardware and software. Back in 2019, when we founded the company, we were asked by many, why another GPGPU or AI chip startup? How could Biren make a difference? To answer this question, we designed BR100 from scratch and centered it around the principles of 5 Cs. First off, we were deeply convinced there was always a necessity to further boost computer density in order to push the boundary of accelerated computing to a newer frontier. As we envision the model size of deep neural networks would continue to grow exponentially, data center compute deficit will also be widened. We thought when BR100 would come out at 2022, it should be roughly 10x performance of 2019 standard. This meant we had to raise the bar from 100 of T-flops to 1,000 of T-flops. That was why we set 1 peta 16-bit mixed precision tensor flops performance as the target, and we did it. Secondly, not only did we need to scale up, but also scale out would also be crucial to solve bigger problems. For instance, brain scale models with hundreds of trillions parameters. We installed high-speed interconnections and can have up to 8 chips fully connected within a server node. BR100 also has the option to connect its 8th link to neighboring node as long as data center infrastructure allows. The third thing is cost. We believe the higher performance in the long run would always lead to lower overall cost for our customers. As we were so determined to build larger chips, we had to be creative with respect to packaging to make BR100 design economically viable. Moreover, lower costs can also be measured by better architecture efficiency in terms of performance per watt and performance per millimeter square. We will show many techniques in the second half of the presentation how we employed hardware and software co-play to address real-life optimization problems. Last but not least, we decided to follow best industry practice to meet our customer growing demands. BR100 uses latest OCP standard OEM form factor. OEM has better interconnection capabilities and a higher power budget, therefore higher compute density. BR100 also supports all popular data formats to make applications compatible with our platforms. With 5 Cs in mind, one key decision we made back in 2019 was to use one tape-out for multiple products. The obvious benefit was that we could break radical size limit and integrate more transistors into a chip. In addition, smaller individual die yields better and lowers cost further. We use most advanced die-to-die technology, which has nearly 900 gigabytes per second bandwidth to ensure inter-die communication transparent to end users. Compared with a hypothetical radical size design, BR100 has 30% more performance and 20% better yield. More importantly, we are now capable of leveraging one tape-out to form multiple SKUs. Here comes the overview of current BR100 product line. The 2-die design, or flagship BR100, comes with OEM form factor at 550 watts TDP, with 8 such chips fully connected within a node on a universal OAI baseboard. It is the most powerful GPGPU server in the world, purpose-built for AI. The single-die implementation is in a commonly seen PCIe form factor. It can be easily deployed in servers for different use cases. We are also closely working with our ODM and OEM partners to build reference cluster designs to make large intelligent model training more accessible to our customers. With that, I will hand over to our CTO, Mike Holm, to give us a deep dive into BR100 architecture.
Hi, this is Mike Holm, CTO of Biren Technology. It's my pleasure to introduce architecture details of BR100 GPGPU. BR100 is designed for data center, AI training, and inference. We have 2 design goals for BR100. The first, it needs to reach 1 petaflop horsepower. The second, it should be a GPGPU, not a pure AI accelerator, which means we will provide our C compiler, which will be able to compile kernel written by OpenCL-like language for better programmability and easier to be compatible to the ecosystem. Let's have a big picture first. BR100 is a chiplet design with 2 computer time and 4 HBM2E stacks. The 4 HBM2E provide over 1.6 terabyte per second bandwidth. The computer tie is fabricated by TSMC 7nm with silicon area about 537 mm². The 2 computer ties are connected by 112 GHz PAM4 high-speed SerDes with bidirectional 596 GB per second bandwidth. With this kind of bandwidth, the 2 ties can operate like one SoC. The PCIe Gen 5 interface can deliver 128 GB per second bandwidth from to host. The 864 GB per second inter-GPU ports can deliver total 512 GB per second bandwidth. 7 of the ports can connect to the other 7 GPU in an OEM system to form a point-to-point connection. Unlike traditional GPU, usually populated with relatively small L2 in the middle of the chip or near the memory controller on the side, BR100 with 256 MB global shared on-die L2 cache associated with each computer cluster and connected by a 2D mesh like NOC system with multitasking capability. The NOC can multitask waits for data parallel and also can multitasking activation for model parallel. This distributed cache and data transfer system capable to provide enough data bandwidth to nearby and older computing core for best efficiency. The average data transmitting distance got significantly reduced. Take a closer look at BR100 streaming processor cluster, HPC. Each HPC contains 16 EU and 16 tensor cores. The tensor core in each HPC can deliver 32 teraflops for BF16 format, 64 TOPS for IN8. The 8 MB SRAM nearby, which can be flexible configured as global shared L2 cache and the strategy pad of the HPC. BR100 is a GPGPU. It can run general computer kernel. There are 16 streaming processor vector cores, 4 special function units, and 1 tensor core inside each EU. We design vector core as a SIMT processor with full set ISA to ensure our GPU's general purpose computing capability. You can have up to 8 warps in each EU, or 128 warps in each SPC, or 4K warps, or 120K computer threads running on 32 SPCs concurrently. Multiple EU can form a CU, or somebody say compute unit. Unlike typical GPU, which usually have 4 EU formed as a CU or SM. However, in BR100, you can have very flexible CU configuration. So you can have 16 EU as a CU, or 8 EU as a CU, or 4 EU as a CU. So with this kind of flexibility, you can allow all the warp in entire SPC synchronize the instruction execution inside a computer kernel. This allows SPC efficiently run multiple kernels in a pipeline manner inside one SPC. Another unique innovation inside the EU is the cooperative warps, or CWAP. Traditionally, different warps inside each EU has its own dedicated register file and cannot be shared throughout the lifetime of the warp. The data sharing between warps must through shared memory or cache system. The CWAP in BR100, however, can share their register value between warps as far as they are in same EU and well synchronized. This unique CWAP concept allows any data transfer between different kernels. The data sharing can happen right inside the local register if they have producer and consumer relationship. This allows SPC easily fuse the data among different tensor operations with tremendous PPA gain. The CWAP feature is especially useful for a case such that you have multiple, say, 2 asynchronized producers with 1 consumer. It's very difficult for a programmer to write an efficient code without CWAP feature. The T-code is designed to speed up the most commonly used operation in AI, such as MMA and convolution. This calculation usually accounts for over 80% of workload in deep learning. Lots of PPA gain in BR100 comes from the design of the Jiang, which has a much better data reuse rate with its output stationary design and less SRAM access. The T-code inside EU can do 128 DP8 and add operation for BF16 format, or 128 DP16 and add operation for IN8. The 16T core form a 4x4 2D 6-dotted array, so we have a hybrid 2.5D GM that 2 64x64 matrix multiplication in 16 cycles for BF16. Compared to normal GPU's small tensor core, BR100 has better data reuse compared to the huge GM from AI Accelerator offer from Habana or Google. This GM has less granularity loss, 1/4 of execution latency, and will integrate with vector core. TF32 is introduced by NVIDIA A100 GPU to enhance AI training throughput while have 8-bit exponents instead of 5 bits for better dynamic range. However, lots of the algorithm developers say TF32 precision is not good enough because it still only has the same precision bits as FP16. So we introduced a new TF32 plus data format. This is a 24-bit floating point format, which has 8 exponent bits and 15 multi-sub bits. The format has the same dynamic range as the TF32, while it has 5 more multi-sub bits. TF32 Plus is 32 times more precise than TF32, making it more effective for almost all AI model training. This format has been efficiently implemented inside our tensor core. It has 1/2 of BF16 throughput, which means it can reach 512 teraflops for TF32 Plus format. TF32 Plus data format can be automatically initiated as while the developer use our tensor acceleration library and declare it as FP32 format. Some developers, in order to get a 0.1% better click rate, may not even willing to compromise their data precision even with TF32 Plus. Do they really only need to get their matrix operation with the vector engine, which usually means 1 magnitude less computing throughput? The answer is no. We have an efficient FP32 tensor implementation. We can have 1/4 of BF16 flops performance with FP32. That means we can achieve 256 teraflops with FP32. NVIDIA FP32 tensor performance emulated with 3x TF32 only can achieve 1/6 of FP16 performance. As I mentioned above, bigger distributed cache, bigger GEM, CWOP innovation, and multitasking through NOT are the key features for more local data reuse. Less data movement across long wire, which save bandwidth and improve power efficiency. However, another key element is really how to make all the data sync and the movement work. The TDA is used to accelerate the data movement from to different RAM and synchronize this data movement with all the SPC in the device or the SPC in the entire computer node. The TDA can do address calculation and out-of-bound check with tensor description. It hides all the detail of the tensor from kernel code for things such as tensor layout, format, whether it is compressed. SPC does not need to babysit thread synchronization among SPC inside the GPU or multiple GPU inside compute node. TDA offloads the SPC's ALU resources and improves the end-to-end performance significantly. For a huge chip like BR100, it's a bad idea to uniformly distribute all the tensor data throughout the entire chip due to long latency. It will lead to more not linked bandwidth and power consumption. As you know, the training sample and its intermediate results are usually private and better saved locally to the HBM or L2 cache close to the SPC, which use it. BR100 built in a steam which time broadcast activation to the relative HPC when multiple HPC run model parallelism with the same training sample. Although weight and weight gradient are human in nature, you can still duplicate them with multiple copies if you want to balance HBM size and data access latency. The idea behind the near memory computing is doing the data tabulation right close to the L2 or HBM instead of read and data back and forth between tabulation unit and the storage component. The near memory computing engine not only can do multiple kinds of reduce operation to speed up or reduce and the bit matrix multiplication, it can also map the embedding table in a way so that the L2 cache can do multi-hot pooling, gradient summation, and concatenation, which is essential for sparse embedding table lookup and update in recommendation system. I also would like to introduce our software stack, Biren Super, including firmware, driver, programming platform, framework backend, SDK, and end-to-end workflow. The programming platform lies at the center of the whole stack and plays the most important role in BR100's programmability. We developed Super, a C++-like programming language with extension and runtime API for developers who are familiar or good at CUDA. They should have no any problem to use Super to define their own operator because we will also offer highly optimized DNN and BLAS library for developers to use directly. We also provide our library to cover general computer library for developers who are familiar with CUPS and shreds. Beyond that, we support mainstream AI frameworks such as TensorFlow, PyTorch, and PaddlePaddle. On top of that, we are building SDK for training, inference, and other application workflow, such as AutoStream for computer vision pipeline and SuCTR for recommendation system. To summarize, first we introduced BR100, a GPGPU designed for accelerating Datacenter scale AI computing. We went over its spec, architecture, and explored HPC in detail. We briefed the TF32 plus tensor data format. Then we introduced several features in BR100 to optimize data flow and improve bandwidth and energy efficiency, such as TDA, CWAP, NUMA, and near-memory computation. Last but not the least, we introduced Biren Super, a software platform for developers to program on BR100. We highlighted the program platform, which has a programming model, library, tool, and compiler. That's all my presentation. Thank you for listening. We are looking forward to working with customers around the world.
Thank you, Lingjie and Mike, for sharing with us the details of very interesting Biren BR100 GPU. Let's take a look at some questions, and also thank you for being available for the questions. They're both joining from China. It's really late at night for them. So the first question is from Joshua Gregory, Chips and Cheese. For matrix operations, does the GPU support sparse matrices? And if so, what are the compute throughputs when you compare sparse versus dense gems?
Yeah, the number we show is the dense flop. Yeah, we do support the structural sparsity, but the performance is the same as the dense actually. And so we just try to have better, power efficiency, but not the faster speed.
Thank you. The next question is from Ashutosh Dar, NVIDIA. Could you please share your target clock frequency?
1 gigahertz.
Thank you. So the next one posed also from Ashutosh Dar, NVIDIA. You mentioned that B-Link can connect to external node. Is it over dedicated link or over Ethernet, PCIe, InfiniBand? What's the connectivity?
It's dedicated.
Sorry?
Oh, it's a dedicated link.
Dedicated link. Thank you. There are also a bunch of questions about programming model. I know you've showed the slide about how your software stack looks like. There are questions if you can run CUDA code, if you can run OpenCL. Can you speak a little bit to that?
Mike will answer this question.
Yeah, it can run OpenCL. We do provide OpenCL compiler. We also provide our own programming. The model is we have our super language. Okay, the super is similar as the other SQL, something like that. And also very similar to the CUDA too. The developer who are familiar with the CUDA can easily write the code to the super.
Thank you. There are also several questions, I think similar to what AMD has been asked. If BR100 show up as one GPU or two GPUs to the software layer?
One GPU.
Thank you. One other question also from Ashutosh Dar at NVIDIA. Is the L2 cache shared across dies or is it private to each die?
It's shared. It can be copied. It can all be shared by all the SPC in the entire, the GPU or entire node. Actually, you can access from other device. SPC can access other device L2 too.
Thank you. One more question from Mahisha Hartikar, NVIDIA. The overview slide showed support for CXL. Can you comment on which devices and which interfaces has been tested with the CXL?
Well, I will answer this question. So our IP does support CXL, but we are still waiting for Intel to release their latest version of CPU, which can support the CXL.
Thank you. So let me check some other upvoted questions. So there is also a question from Ronny Krashinsky, NVIDIA. Does each L2 slice cache data that is local to SPC accesses? So essentially, is coherence managed on per line basis or per bulk cache?
Yes, it's coherent. Yeah, the L2 cache, each SPC, has it has its own neighbor L2. It has a dedicated bus, can read direct to the L2, and if the other SPC try to access that particular L2, it must go through the NOC.
Thank you. One more question from CC Jiang at Grok at Stanford. Can you please share how much TF32 Plus boosts AI training inference due to their extra 5 bits precision?
Yeah, actually, a lot of developers say they wanted to have, they don't have patience to try to, to optimize the length of the data format. So they asked for this flexibility. We provided flexibility. Yes.
So do you have any comments on performance? No.
We are based on our experiments, it's easier to convert. Yeah.
Okay, thank you. One other question from NVIDIA, Umur Darbas. Do you support L2 to L2 communication across SPCs?
Yes, the SPC share the data through the L2 cache,
Okay. One more question from Thompson Jones at Cruise. He's actually asking if we can expect to see MLPerf submissions to support the performance claims that you've shared, and given your affiliation with ML Commons.
Yes.
Sure, yeah. Actually, we already submitted to the latest round of MLPerf inference, and you should be able to see our results in 2 or 3 weeks.
That's really cool. Looking forward to it. One other question. So on the slide, you shared performance comparison versus A100. Can you share what it is for training or inference?
Oh, they include both training and inference. And for the ResNet and the BERT results, we use MRPerf standard settings. And for the other models, we use our customers' in-house customized models. And like I said, you should be able to see the MRPerf submission results pretty soon. And we're working pretty hard for the MRPerf training submission as well.
Cool. Thank you. Let's thank Lingjie and Mike for a really great talk. They mentioned it's really late for them. They promised to get back to answer all questions on Slack when they wake up. It's the middle of the night for them. Thank you, Mike and Lingjie, for joining us.